Hey, Edward.
How you doing, Professor?
Hey, Edward. How's it going?
Not too bad. Just a little tired.
Yeah. We have Monday off. I didn't know that. Or
I didn't know that. I didn't know that until today.
yeah. So that would be nice. Although it was funny because I knew that before the semester began because I planned for it in my schedule, but then it just slipped my mind until someone reminded me today.
I didn't see it anywhere in like any like class syllabus, like class syllabi or um yeah. And then someone just mentioned it in class today, so pretty excited about it.
Yeah. Long weekends are always appreciated.
Hello, Professor.
Hey, how's it going?
Sir, how are you?
Good, good.
So I just have a quick question in regards to the homework.
Okay, sure.
Did you end up choosing the problem you're going to grade?
Oh, for homework one,
Yeah.
I have not. So I'll probably grade those tomorrow, and then I'll decide tomorrow which one I'm going to grade.
Oh, I see. Oh, and in for today's class, I might be leaving early
Okay.
because I have an appointment. Just thought I'd let you know.
Okay. Yeah, thanks for letting me know.
Yeah, it was just out of the blue. I was very lucky that I got the appointment. I literally just got the call like
Oh,
half an
dang.
hour.
Nice. Is it for an interview or what's it for?
No, it's my second dose for the vaccine.
Oh, okay. Oh, great, great.
Yeah, so I was
Appreciate it.
trying to find a slot, and then they're like, actually, I have an opening at 3:15. I was like, okay, I'll take that.
Nice. That's good. That's good.
Yes, sir.
Yeah, definitely good to get that get that out of the way.
Yeah, it's my second dose. Hopefully, it goes as smooth as the first one.
Was your arm sore or did you feel sick after the first dose?
It was just like the soreness of the arm, and
Hmm.
then it was like you got tired faster.
I see. I see. Okay.
But I didn't get a headache or a fever or a nausea.
Okay. That's
But
good.
it was just more of like tiredness.
Mm.
And just like after a long day of work, as soon as you get home, you just want to sleep.
Yeah, that's
You're
true.
just constantly in that feeling, regardless of what you're doing, and the soreness.
That's good. It seems like it didn't affect you too heavily.
Yeah, hopefully the second one doesn't.
Yeah. So the lectures are recorded, so you can always go in and watch them afterwards. So that's one of the nice things I like about this virtual teaching is that the recordings
Yeah,
you can go back and watch
it's
them
always
afterwards.
good to
So
make sure to let you know. It's just I don't know, it's just like etiquette, I guess.
oh yeah, I think it's definitely good. Um, yeah, it's good just to have a heads up. So.
Yes, sir.
Mhm.
Any plans for the weekend, sir?
Uh, it is Lunar New Year this weekend, so I might hang out with some of my fiance's family. My family, we're not planning anything because usually we like to do a big family gathering, which obviously we can't right now. Um, and so I think I might
So
just hang out with my fiance and her brother and his wife.
it's also Valentine's Day.
Valentine's Day, yep. You figure out what I need to what I'm going to do for Valentine's Day.
And it's gonna be a pretty busy weekend.
Yeah, it's a good thing we have Monday off because
Oh yeah.
that'll be nice.
So, Professor, for this class,
Mhm.
like how or what is the required, or like how do you get an A, or how can you get an A in your opinion? What should you do?
I mean, if you look at how the grades break down, there a lot of the weight is obviously on the exams, and so we have
Yeah.
our 2 midterm exams and we have our final exam, and so doing well in the exams, obviously you're going to do well in the class. But for my exams, I typically write them to be a little bit easier than the homework. So I know I go a little bit intense on the homeworks. I ask pretty tough questions and pretty long and involved questions on there, but I do that on purpose so that because my feeling is that with the homework, it's not a time constrained thing. Like you have, I give you at least a week to work on it, and so that's why I feel like I should really challenge you guys and ask you guys tough problems. The exam is something different because an exam, you're sitting there and it's kind of a stressful thing because you're only going to be there for like an hour and 15 minutes. And so I tend to ask a little bit easier questions on the exams. And so usually my advice for preparing for the exams is always, go through your homeworks, not only, get to the answers, but, really understand like every step in the process of, why you did this and conceptually kind of understand all that. Because if you can do that, then, the exams will be kind of one level below that. Before every exam, I also do a study guide. And so I give you guys, just a PDF of, these are all the topics and these are all the learning objectives that I'm going to expect you guys to know for the exam. So definitely do all of that. And so, just keeping up with the homeworks and, making sure you're studying adequately for the exams. That's usually the best advice I can give to people.
Are you going to be uploading like the full worked out way to solve the homeworks?
Yes. Yeah. So I usually upload those right after I grade them. And so right now I was taking care of some stuff today. So I plan to grade your guys' homeworks tomorrow. And so you can expect the solutions for homework 1 to be up by tomorrow evening.
Okay, thank you.
Yep. Mm-hmm. No, we don't. So Monday is a holiday, so we're not gonna have lecture on Monday. Yeah. I will have my office hours on Monday, and so if you want to come in and ask questions, I'll be there from 9 to 10. But we're not gonna have lecture on Monday because it's a school holiday. Okay, it's 2:30, so let's go ahead and get started today. All right, good afternoon, everyone. How's everyone doing today?
Doing pretty good. How are you?
Good, good. Yeah, doing well. Yeah, it's the end of at least the end of our week, which is always a little bit strange because this lecture ends on Wednesday, which is kind of the middle of the week. But it's kind of how it is. All right. And so if you weren't here just 2 minutes ago, I know some people are kind of moseying in right now. Monday is going to be a holiday, so Monday I think is President's Day, and so we're not going to have lecture on Monday. And so after today's lecture, the next time I see you guys will be next Wednesday. Right? And so I'm mentioning that now because I will almost definitely forget by the end of class. And so, don't come to lecture on Monday because I won't be here. But I will have office hours because I know that we have another homework due next week. And so if you want to come by on Monday morning to ask questions from 9 to 10, I'll be there for office hours. But, we're not going to have lectures on that day. Okay. Okay, so the plan for today is we had one very small thing to finish up with spherical heat transfer, which is basically just how to set up a thermal circuit with spheres, and then we're going to move on to our next topic, which is heat transfer from fins. Okay, and so fins is kind of a conversational term for just any kind of extended surface, right? And so we'll get into that after that. Okay. And so fins is actually, it's going to take us all of today and maybe about half the lecture on next Wednesday, because there is actually quite a lot to this kind of seemingly simple kind of thing. Right? So before we get started with any of that, are there any questions I can answer? Okay. All right, so remember, the next homework, which is just based on the cylindrical and spherical heat transfer, that's going to be due, I think, next Wednesday at 11:59. So, make sure that you're doing that. All right, so there's one more thing I wanted to cover with spherical heat transfer before we move on, which is thermal circuits with spherical geometries. Okay. All right. So I believe last time we actually derived the expression for the thermal resistance of a sphere, and that was based on one of our solutions to the heat equation, and that resistance was given by the following. Okay. And so we had R sphere is equal to 1 over the inner radius minus 1 over the outer radius divided by 4 pi k. Okay. And so what you have here is another formula for thermal resistance that you can use in basically exactly the same way. Okay, so even though it's a spherical geometry, you can set up the thermal circuit, just like you did in Cartesian coordinates and just like you did in cylindrical. It's just that now whenever you have conduction, you're going to use this equation here. Okay, and so just as an example, let's do a 3-layered sphere. Okay. So let's say that we have a sphere that looks like this, right? And so let's say that all the way up to here, this is our radius is R1, okay? Up to the second notch, our radius is going to be R2. The third notch is going to have a radius of R3. And the fourth notch is going to have a radius of R4, okay? And then inside these layers, they all have a unique thermal conductivity. Okay. Right. And so let's say that we have Ka for the first layer, Kb for the second, Kc for the third. Okay. And then on the outside of the sphere, let's say that we have heat transfer due to conduction or convection. Right. And so that convective heat transfer is going to have its coefficient H and its temperature T infinity. Okay. All right. One more thing that we need before we draw the circuit is we need to know the temperature on this interior surface here. Okay. And let's say that we have this temperature. We'll give it a value of Ti. Okay. All right. And so, from this, you can see that, we have a multi-layered system. So we have heat transfer through conduction through 3 different solid layers. And then we also have heat transfer for convection. Okay. Remember, whenever we have a system with, multiple different layers like this is a great candidate to use thermal circuits for. Okay. And so in this particular case, we're going to have 4 resistors. And so we're going to have 1 resistor for each of the solid layers. Right? Okay. And then 1 resistor for the convection. Okay. Okay. And so, first thing we're going to label in our thermal circuit here are the end temperatures. Right? And so on the left-hand side, we have a temperature of Ti. Okay. On the right-hand side, we have a temperature T infinity, which is the convection heat transfer. Okay. And then for each of these resistors, we're going to write out their expressions according to, the formula that we have above. And then finally, 1 final resistor for convection. Okay. So let's start with the conduction resistances. Okay. And so for layer A, we're going to put in the inner radius for layer A and the outer radius. And so this is going to be 1 over R1 minus 1 over R2, all divided by 4 pi Ka. Okay. Okay. And so that's the resistance for layer A. Layer B, the inner radius is going to be R2. The outer radius is R3. Okay. And then we're going to divide by 4 pi at Kb. Okay. Right. And then finally for layer C, we're going to have 1 over R3 minus 1 over R4 times 4 pi Kc. Right. And then for the convection resistance, remember the convection resistance is always going to be 1 over H times A, where A is the surface area through which we're doing convection, and for a sphere we're going to write out the surface area of the outer sphere. Okay. Right. And so the surface area of the outer sphere is going to be 4 pi R4 squared. Okay. And so there is our thermal circuit through which, we can compute heat transfers, based on the difference in temperature. So kind of exactly as we've done before. Okay. Okay. Any questions on this?
Professor, up to R1, is the sphere hollow or is that solid?
Yeah,
you
so
have
it's
the TI?
Yeah, good question. So that's up to R1 right here. The sphere is, we're going to assume that it's hollow on the inside of R1.
Okay.
Yeah. Mm-hmm. All right, any other questions on this before we move on to fins?
With that, could you have a convective heat transfer in the hollow sphere, or is that?
Oh, definitely. Yeah. So if you, it's a little bit hard to do because on the inside of the sphere, it's a little bit hard to get flow going. But absolutely, if you have some kind of flow on the inside of the sphere, maybe you're injecting something on the inside and that's causing it to swirl. You can definitely have convective heat transfer on the inside of the sphere.
Okay.
Mm-hmm. Right. Okay. So that's, everything with radial heat conduction. Okay. So now you should be fully equipped to do the homework. Okay. And this example in particular right here, I know we didn't put in any numbers, but this geometry should look very similar to the last problem on the homework, which examines, actual heat transfer from your eyeball. Okay. So your eyeball is one thing that, you could have, it's not exactly a sphere, but it's close enough to a sphere that we can approximate it as such. And we can use these ideas to compute heat transfer from your eyeball. So hopefully that should be an interesting problem for you guys. Okay. Okay. And so now we're ready to move on to the next topic, which is heat transfer from extended surfaces.
Wait, Professor, I have a quick question
Sure.
about the last example.
Mhm.
So just for that example alone, are you just supposed to set it up just like that? That'd be like the final answer?
So this is just the circuit. So, from the circuit, you'll be able to compute things like heat transfers, right? And so you can set up an equation like Q will be Ti minus T infinity divided by the sum of all the resistances right here.
Got you.
So the circuit here is just a starting point. And so once you have the circuit, then you can use it to, solve for heat transfers, or maybe you're interested in like a temperature like right here, right? And so I think for the homework problem, I asked you to solve for, what's the temperature on the surface of your eyeball, right? And so, this circuit here will kind of just be a starting point for how you can, solve for a bunch of other stuff. Yeah.
Okay, thank you.
Okay. So heat transfer from extended surfaces. Okay. All right. And so this is kind of the formal name for this unit here. But kind of the informal name, which is what most people use in practice, is any kind of extended surface off off an object is known as a fin. Okay. Right. And so you'll see me. So I'll use fins for kind of the rest of this unit because it's a lot easier to say than extended surface. Okay. Okay. And so let's talk about first of why do we have kind of a separate unit on fins compared to the other stuff. Okay. And so the reason for that is up to this point, we've assumed that the heat transfer was purely one-dimensional. Okay. Right. And so this was an extremely important assumption for us because it allowed us to like really simplify the heat equation. Right. And so just as an example, we've looked at cases like maybe heat transfer through a layered wall, right? And maybe we have convection on the outside here, okay? And so the heat transfer we assumed is all in this direction. Right? And so even to the fluid right here, right? So we assume that the heat is going to leave the surface and is going to go out to the fluid in that direction, right? And so everything is in just one direction. Right? Okay. And so with extended surfaces, we're going to have something different. So we're actually going to be in a kind of a pseudo 2D case. Right? It's not going to be general 2D heat conduction, but we are going to have heat transfer in different directions here. Okay. And so what we have now is something like this. Right? And so let's say that we have an object like this, right? And so let's say that our top surface here is held at T1 and our bottom surface is held at T2, right? And if T1 is greater than T2, we know that we're going to have conduction heat transfer going this way. And so heat is just naturally going to flow from high temperature to low temperature. Okay. Okay. But the wrinkle that we're going to throw in here is that now let's assume that we have convection. But now the convection is going to be blowing across this surface. Right? And so we're going to have, heat transfer by convection like that. Right? And so, if you actually look at how heat is going to leave this solid to the fluid, you'll see that, it's going to look something like this. because the fluid is kind of touching the surface on its lateral side instead of at the end, our heat transfer due to convection is going to go left and right. Okay, and that's different than when the heat transfer is going down the length. Okay, and so now what we have here is a kind of a pseudo 2D situation where our convection is going one direction, but our conduction is going the other direction, right? And so the methods that we've developed up to this point, won't be able to apply here because we can't assume that all of it's in the same direction. Okay, and so we're going to need to come up with a different equation. So we'll come up with a what's called the fin heat transfer equation, and then we'll discuss how to solve that. Okay. All right. Any questions on this? Okay. All right. So before we do that, let's talk about just the general purpose of fins to begin with. And so usually, if you're designing your engineering device, the reason why you would want to add fins to a surface is you want to enhance heat transfer. Okay. Okay. Because in most of these situations, you're going to have some kind of fluid. A lot of times it's air, right? So you just have air blowing over your device, right? And if you want to enhance heat transfer from your engineering device to the fluid, right, then you want to add some fins, okay? And the primary way that fins enhance heat transfer is that they just simply increase the amount of surface area that is on your object, right? All right, question in the chat, like the World War I Lewis machine gun. Yeah, actually, like a lot of those, I think a lot of those early gun designs needed fins just because those things just heated up like crazy. And so just to prevent them from burning the operator's hands or melting themselves, they had to put fins on them so that they could, expel their heat a lot more efficiently. Okay. Because in general, the more surface area that you have, the more opportunities or the more places that convection can take place. Okay, and so just as a very simple example, let's consider a surface like this. Okay, and we have fluid that's blowing past it, right? Okay, and so since we have fluid that's flowing past the surface right here, we're going to have convection heat transfer. Okay, and so heat's going to come out here to the fluid. And so that's fine. But then what if we have a surface that looks like this? Okay. Right. And so in terms of height, you can see that these guys occupy the same kind of vertical space right here, right? But, the case on the right just has a lot more surface area, right? And so when you blow fluid past this guy, whether it be air or water or whatever, okay, you're just naturally going to have a lot more convective, heat loss from this guy because you have much more surface area, right? So, there's basically much more places for heat to escape the system due to convection. Okay. And so this concept is actually used a lot. And so you'll see fins, in a lot of computers actually too. So in computers, you'll see kind of these structures that kind of just seem to come out. So usually they're made of metal, right? And they don't plug into anything. But what they're used for is just to, again, increase the surface area of whatever computer hardware, computer chip that you're on, okay? And that increased surface area will help cool it, much more efficiently because you have much more surface area, okay? So you'll see fins that are used in engines as well, right? So particularly on motorcycles. And so, fins are used to cool motorcycles pretty efficiently, right? Also in just any kind of air conditioning or heaters as well, yeah. Question. So I'm guessing there's a sweet spot for the distance between the fins. Yeah. So we'll talk about that. Probably not today, but probably next Wednesday we'll get to that. And so we'll talk about fin performance and different ways that you can optimize that. Yeah. Mm-hmm. Okay. And so, you know, if you end up, you know, working in any kind of thermal engineering, you know, odds are, you know, you're going to be working with fins to some degree. Okay. Because you know they're relatively very simple, but they're just also just very effective. Right? So if you know how to analyze fins, you know how to design them, you know that's kind of a big part of you know the thermal engineering for a lot of different devices. Okay, and so what are we particularly interested in as engineers? So as engineers, what we're interested in is you know is computing how much heat is transferred from a fin. Because if you can compute this, you know, how much heat is lost from a fin, then you can, you know, learn how to design them and, you know, make them a big part of your engineering design. Okay. Okay. And so in order to compute the heat transfer, you know, just like up for everything up to this point, we're going to need to know the temperature distribution in the fin. Okay. Because if we can solve for the temperature distribution, computing heat transfer is just a matter of either doing Fourier's law or Newton's law of cooling. Okay. All right. And so what we're going to do next is we're going to look at the fin heat transfer equation and then look at the different terms. So we're not going to derive it, you know, because you know I think that would take a bit too long. But you know we can at least look at the equation and talk about each of the different terms in there. All right. So before we do that, are there any questions on this? Okay. All right, so let's look at the fin heat transfer equation. And so I'm going to write out the full equation right now, but you know we'll simplify this significantly, you know, as we apply some assumptions. Okay. And so the first thing we have is d squared t dx squared. And so that should look familiar. So that's a remnant of our regular heat equation, right? So if you remember from our regular heat equation, we had the second derivative of t with respect to x. Okay. Okay. The next thing that we have is this term. So we have 1 over AC times dAc dx times dt dx. Okay. And so AC in this case is our cross-sectional area for the fin. My phone's ringing. Someone's about to tell me my social security number has expired for the 11 millionth time. Okay. And so that's the second term. And we have one more term here, which has to do with the outer surface area. Okay. So it looks something like this. Okay. And all that's going to be equal to 0. Okay. All right. And so we've introduced another new variable here, which is AS. Okay. And so AS here is going to be the outer surface area of the fin. Okay. And so let me draw just a quick figure here just so that you kind of know the difference between AC and AS. Okay. And so our typical fin looks something like this. And so let's say that we have a cylindrical fin. Okay. Right. So AC will be this area, right? So if we take kind of a cross section of the fin, that's the area that I mean by AC, right? AS will be kind of the total outer surface area of the fin, right? And so that's the surface area all around the outside right here. Okay. And so that's our fin heat equation right there. Okay. So let's talk about each of the different terms in this equation, and then we're going to cancel out. We're going to simplify this significantly with our assumptions. Okay. All right. So first, let's look at the first term, right? And so this first term right here, like I mentioned before, is a remnant from our regular heat equation, and this just represents spatial diffusion of temperature along the fin. Okay. And so our fin, is it's made of a solid material, and so because of that, we're going to have heat transfer through conduction all the way through the fin, and that's what that first term basically represents. Okay, so it looks exactly the same as the term that we've had previously, because it represents the same thing. So that first term basically represents heat transfer through conduction through the solid part of the fin. Okay. Okay. Now let's look at the second term right here. Right. And so what the second term represents is it's actually a change in heat transfer in case the cross-sectional area of the fin changes. Okay. And so the key term in this second term is this dAc dx. Okay. And so what that term mathematically represents that if the cross-sectional area is changing as we move along the fin, and so say that you have a case of a fin that tapers, right? And so let's say that we have a fin that might look like this, right? And so in that case, the cross-sectional area is changing with respect to x, right? Then this term kind of accounts for that. So you can almost think of the second term as almost like a correction factor to account for the fact that if we have a changing cross-sectional area, then mathematically we can account for that, because that's going to affect the heat transfer. Okay. Okay. And then the last term right here, this represents the convection heat transfer on the lateral surface of the fin. Okay. And so, because this fin is, a very slender object, our convection heat transfer is going to take place on the outside. Okay. And that's what that term represents. And so this one equation right here kind of accounts for those kind of three modes of heat transfer. So we have regular conduction through the fin. We have a correction factor in case the area is changing. And then we have a term that deals with the convection heat transfer off the lateral side. Okay. Okay. Any questions on this so far? Okay. So let's go ahead and start applying some assumptions here to simplify this guy. Okay. And so the first assumption that we're going to make, which is, I think fairly, fairly common, or it's not that bad of an assumption. We're going to assume that the cross-sectional area does not change. Okay. And so we're going to be dealing with a fin that looks exactly like the one I have pictured here. So it's basically the same cross-sectional area all throughout, right? And so if the cross-sectional area doesn't change, what that tells us is that the derivative of AC with respect to x, that term is going to be 0. Okay. And so what that will allow us to do is just, it allows us to cancel out this entire second term right here. Okay. Which is great because, you know, now we don't have to deal with it at all. Okay. All right. And so if the cross-sectional area doesn't change, that actually allows us to simplify this derivative right here on the right, which is dAs dx. Okay. And in particular, we're going to put this in terms of the perimeter of the fin. Okay, but I'll do that on the next slide because this one's getting a little bit crowded. Okay. And so if our cross-sectional area doesn't change, you know, our fin might look something like this. Okay. Okay. And let's assume for a second that we're considering, you know, a length of the fin denoted by x. Okay. Right. And so we can say that the distance from the base of the fin over to this section of the fin right here is x. Okay. One other thing that we're going to know here is we're going to know the perimeter of the fin. Okay. Okay. Because if the cross-sectional area is constant, then the perimeter will also be constant as well. Okay. Okay. And so let me do this. So up to this point x right here, let me go highlight the surface area that we've covered so far. Okay. Okay. Right. And so if we only consider, you know, the section of fin that we've covered up to a distance x, we can compute the surface area up to that point. Okay. And so we're not considering the whole fin here. We're just considering the section between, you know, the base of the fin over to x location of x. Okay. We can then compute the surface area from this. It's just going to be simply the perimeter of the fin multiplied by whatever distance x. Right? Okay. So this is the part that's a little bit strange because it's, you know, we have to kind of think about, you know, how the surface area of the fin, you know, varies from different x locations on the fin. Okay. And so this function right here is, you can almost think of it as the surface area that we've swept out as we travel from the base to the end of the fin, right? And so if we're a distance of x from the base, we've swept out a surface area of p times x. Okay. Are there any questions on that?
What if you have like a hollow tube?
Yeah, so if you have a hollow tube, that's going to affect mostly your cross-sectional area. And so if you have a hollow tube, then you're not going to have any convection heat transfer in the middle. And so you're still going to have, you know, convection heat transfer off the outside. It's just going to affect, you know, the cross-sectional area for how much conduction is going to go down that way. Yeah. Mm-hmm.
Would that be the case if it were like a hollow tube that was like had a hole in it rather than like being sealed?
Yeah, it would still be the case because it's if you kind of slice it, you know, if you slice that hollow tube all the way, you know, then you're still going to get kind of the same cross section all throughout. Yeah.
For the perimeter, would you count the inner surface area too for the tube?
Yeah, good question. In that case, you wouldn't. So you would only count the outer perimeter because that's the part that's basically interacting with the fluid.
Oh, okay.
Mm-hmm. Although you bring up an interesting point though. So if it is a hollow cylinder, you might have a little bit of airflow going into the tube, depending on, you know, what's on the inside of the surface. And I imagine that's probably a clever thermal design that I think some engineers might take advantage of. But you know, in that case, it might get a little bit complicated because you would probably have a different convection heat transfer coefficient outside the cylinder versus inside. But I'm sure that there's designs out there that take advantage of that. Okay, and so if this is our formula for AS, we can compute the derivative of it. And so dAs dx is just going to be P, our perimeter. Right? And this is something that we can plug into our fin equation. Right? And so our fin equation, you can see that I've circled in green right here, we have dAs dx. Right? And so for the case when we have a constant cross-sectional area, then dAs dx is also going to be a constant, which is just P. Okay. And so if we put all these together, we can get a much more simplified version of the thin heat equation. Okay. Okay. And so we have our first term, which is d squared t dx squared. So that's fine. Right. Then we have h times p. And so h, remember, is our convection heat transfer coefficient on the outside. P is the perimeter that we just talked about right here. Okay. Then we have K, where K is the thermal conductivity of the material, of the fin material itself, times the cross-sectional area. Okay. Then we have the difference of between the temperature of the fin and the surrounding fluid, and all that's going to be equal to 0. Okay. Okay. And so you can see here we have a much simpler equation right here to work with. Right? And so just to kind of remind you what each of these terms represent, this first term right here is conduction heat transfer down the length of the fin. And then the second term right here is convection heat transfer off the outer surface of the fin. Okay. And the nice thing about this equation that we have here is that these parameters here, which I'm going to circle in orange, all these guys are constants. Okay. And so what we simply have here is a second order differential equation. It's a bit more complicated than our usual, heat equation, but this is something that we can solve, right? But there's actually, one more thing that we can do to make this a little bit simpler, okay? Because right now this is what's known as a non-homogeneous differential equation, okay? In other words, we have a term out here, this T infinity times HP over KAC, that's going to make solving this, more difficult than it has to be. And so what's typically done for fins is we're going to make a change of variables to simplify this a little bit more. Okay. It sounds scary, but it's one of the simpler change of variables out there possible in science. So it's actually going to make our lives a lot easier once we do this. Okay. So before I do that, are there any questions on this page here? Okay. Okay. And so let's go ahead and define our change of variables, right? So we're going to define a new variable called theta, right? And we're going to define theta to be like this. Okay. And so theta is just going to be the difference between T of x minus T infinity, okay? Where T of x right here, this is the temperature in the fin at a position x. Okay. Okay. And T infinity, this is the temperature of the fluid. Okay. Right. And so the way that we've defined theta here is that theta here is what's known as the excess temperature. Okay. Okay. And so the excess temperature is basically defined as how much hotter is our fin than the surrounding fluid. Okay. And so if you take the difference between the temperature of the fin versus the temperature of the fluid, then you get the excess. And so that's kind of, you know, whatever the fin is in excess of the fluid. Okay. Okay. And so this will help us simplify our equation, because now what we have to do is if we, you know, take derivatives of this. Okay. And so let's say that, you know, we take two derivatives. Okay. And so let's say that we do d squared theta dx squared. Okay. And so we take the derivative of the above expression twice, right? And so for the first term, we get d squared t dx squared. Okay. And then when we take the derivative of t infinity twice, you know, we just get 0 because, you know, we're taking just the derivative of a constant right there. Okay. And so what this will allow us to do is it'll allow us to come up with an even simpler version of the fin equation. Okay. Because what that'll do is that'll eliminate this non-homogeneous term on the right here. Okay. And so then we'll just have d squared theta dx squared minus hp over kac times theta. And this is a much easier equation that we can solve. Okay. Right. But before I move on to that equation, I want to talk about this set of parameters right here. And so let's go look at that on the next page. Okay. And in particular, I want to look at the terms on the top of this expression versus the terms on the bottom of the expression. Okay. All right. And so on the top right here, we have H, where remember, H is our convection heat transfer coefficient multiplied by P. Okay. And so what this is, these are all parameters that have to do with only convection heat transfer. Okay. Because if you think of it like, you know, if you increase H or you increase, you know, how effective the convection is, you're obviously going to increase the amount of convection heat transfer that comes out. But also, if you increase the perimeter of your fin, that's also going to increase the amount of convection because that increases the surface area, right? And so on the numerator of this expression of this parameter here, you know, we have variables that only affect conduction, okay, or convection, sorry. And so if you compare that to the denominator, on the denominator here, we have thermal conductivity multiplied by the cross-sectional area, okay? And so these are expressions that only affect conduction heat transfer. Okay. Because if you increase the thermal conductivity of the fin, that will increase the amount of conduction that goes, you know, down the length of the fin. Likewise, if you increase the cross-sectional area, that, you know, increases the amount of conduction that goes there as well. Okay. And so basically what you have here is you have a ratio of the strength of basically the strength of convection of the fin over the strength of the conduction of the fin. Okay. And so you have convection over conduction. And so since this is a ratio here, we often give it, you know, a special symbol, again, to kind of simplify our work, okay? And so for the purposes of this analysis, we're going to assume that we're going to replace this quantity HP over KAC with a new variable called M squared, okay? So I know it's a lot of you know, variable replacements here, but you know, in the end, it's going to simplify our equations. And then once we actually go start to solve it, you'll see kind of why we do all this, because even with all these simplifications, the math is still going to be pretty intense. Okay. And so I know I'm changing the names of the variables around quite a bit, but that's why I wanted to take some time and define what each of these mean. Okay. And so, just to kind of summarize this section, first thing we're going to substitute is we're going to substitute theta in for T, okay? Where theta here is just going to be the excess temperature, or how much hotter our fin is than our fluid, okay? And then we're going to make another substitution for m squared, where m squared here represents the relative strength of how much or how strong convection is over how strong the conduction is in the fin, okay? And so, from this point on, I'm just going to use theta and m. And so I just, want you guys to kind of remember what they physically represent. Okay. All right. Any questions on this? Okay. All right. And so if we make those substitutions, then our fin heat equation is, probably takes the simplest form ever, right? And so it's just going to be d squared theta dx squared minus m squared theta is equal to 0. Okay. And so this is our simplified fin heat equation. Okay. And so now what we have here is a homogeneous second order ODE, that we can solve much more easily. Okay. All right. And so if you recall from 308, the way that we can solve this kind of equation is to use the characteristic equation. And so if we use the characteristic equation, we're gonna set the second order derivative. We're gonna replace that with a quadratic term. Okay? And so instead of d squared theta dx squared, we're gonna have lambda squared minus m squared. Okay. And this guy is gonna be equal to 0. Okay. And so if we solve for m, or solve for lambda, sorry. What we get is lambda is equal to plus or minus m. Okay. And so with that, we can thus form our general solution. Okay. And so our general solution looks like this, right? And so we're going to have C1 times the exponent of lambda 1 x plus C2 times the exponent of lambda 2x. Okay. And since our lambdas are going to be plus or minus m, we're going to go ahead and plug that in. Okay. And so our solution is going to be theta of x is equal to C1 times e to the mx plus C2 e to the minus mx. Okay. All right. And so a deceptively simple solution, but it's going to get a lot more complicated once we start applying boundary conditions. But before we do that, are there any questions on this so far? Okay. Okay. And so now that we have the general solution here, just like we've done with the heat equation, we're going to need to apply boundary conditions to solve for C1 and C2. Okay. All right. And so the boundary conditions that we're going to apply are going to take place at the two extremes of the fin. Okay. And so if we have a fin that looks like this, Right. So we're going to apply one boundary condition here and one boundary condition here. Okay. Right. And so the boundary condition on the left right there, which is where the fin attaches to our engineering device, this is going to be known as our base condition. Okay. Because that's going to be the boundary condition at the base of our fin. Okay. And then on the other side of the fin, we're going to apply a boundary condition on the tip. Okay. And so this is known as the tip condition. And so
is that a P at the base?
Wait, say again, a P? Oh no, it's just a dot. There you go. Yep.
Oh, okay.
Yeah, my stylus likes to kind of drag down a little bit. Okay. So for the base condition, there's only one option, which is nice, just because it's there's only one thing that we can apply there. And what we are basically going to assume is that we know the excess temperature at the base. Okay. And so what we have at the base is we're going to have theta of 0 is equal to theta b. Okay. And so we're basically going to assume that we know, how hot our device is at the base, and so we can compute, the difference between our device temperature versus the surface temperature. Okay. Okay. And so if you remember, theta represents our excess temperature. So theta b is going to be nothing more than TB, where TB is going to be the temperature at the base minus T infinity. Okay. So this is pretty reasonable most of the time, because most of the time you're building a fin so that you can cool a surface. And so if you want to cool a surface, you kind of already know how hot it's going to be. Okay. And so that's the base condition. And so that's the only one we need to apply there. And so for the tip, there's lots of different conditions that we can apply. And so actually there's 4. Okay. And so I'll go through the derivation of one of the 4 conditions, which is one of the more complicated ones, and then we'll kind of just talk qualitatively about the other ones. Okay. Okay. So before we dive into that, are there any questions on this? Okay. All right. And so this is going to be tip condition 1 out of 4. And so what tip condition 1 states is that we're going to have convection heat transfer from the tip of the fin out to the fluid. Okay. And so we're going to set up an equation here for convection heat transfer, right? And so this is very similar to how we set up, convection heat transfer, in 1D convection, okay? And so on one side of this equation, we're going to have Newton's law of cooling. And so we're going to have H times AC times T of L minus T infinity, okay? Where L here is the length of the fin. Okay. This is going to be equal to minus K times AC times dt dx at x is equal to L. Okay. And so, just like we've always seen with our convection boundary conditions, we have a balance of heat transfer due to convection, which is, on the left-hand side. And on the right-hand side, we have heat transfer due to conduction, okay, which is 4a². And so notice, in this convection heat transfer equation, we have AC right here, okay? And so remember, AC is the cross-sectional area, right? And so basically what we're saying here is that at the tip of the fin, okay, and so if we just consider this area right here, which I'm going to highlight in green, okay, the area of this fin of this tip right here is AC, right? Because that's going to be our cross-sectional area. And so what we're assuming with this boundary condition is that at this tip, we're going to have convection heat transfer. Okay? And so this is separate from, the convection heat transfer that takes place over the body of the fin, right? Because we know that at the same time, we have convection heat transfer that goes across all those orange terms, right? And so this boundary condition just states that, for now, for this boundary condition, we're only saying that we have convection heat transfer off the tip, okay? And so the convection heat transfer for all the other parts of the fin in orange, that's already accounted for in our fin equation, okay? But we haven't accounted for the tip yet, so that's kind of the purpose of this. Okay, and so let's go ahead and simplify this equation. First of all, we see that we have AC on both sides, and so we can go ahead and cancel those out. Okay. One thing we can also do is we can replace this T of L minus T infinity with theta. Because remember, that's exactly what theta is. So theta represents, the difference in temperature between the fin and the fluid. Okay. And so the simplified form for this equation is going to be H times theta of L is equal to minus K d theta dx, okay, at x is equal to L. Okay. And so this combined with our other boundary condition gives us two conditions through which we can solve for C1 and C2. Okay. All right.
Professor, I had a quick question.
Yeah, what's up?
That theta of L term, is that like the function representing theta at a certain length, or is that just multiplied times the length?
Yeah, it's the first one. So it's going to be our theta function evaluated at x is equal to L.
Okay. Yeah. Okay, thank you.
Right. So I'm about to warn you guys that this math right now is going to get a little bit intense, because we're going to deal with a lot of exponentials here, probably more exponentials that you ever want to see in your lifetime. But I will say that this tip condition right here is the most difficult one, and so it leads to kind of the most intense math. But if you understand this one, then the other ones, by comparison, are a lot simpler. Okay. All right. So let's start working through the math of this condition. Okay. Okay. And so let me actually write out our base condition here. And so our base condition basically says that theta of 0 is equal to theta b. Okay. And so if we plug in x is equal to 0 into this our general solution here, what we simply get is just C1 plus C2. Okay. So very, very innocent looking so far, right? And so what we can do from this equation is we can basically solve for one of these constants in terms of the other one. Okay. Okay. And so if we solve for C1 in this equation, we get C1 is equal to theta b minus C2. Okay. Right. And so this is going to help us solve for C2 once we apply our convection boundary condition. Okay. All right. So let's now apply our convection boundary condition. And so let's go ahead and apply this guy right here. Okay. And so on the left-hand side of this equal sign, we have H times theta of L. And so theta of L, we're going to evaluate our theta function at x is equal to L. Okay. So we have C1 times E to the m times L, right? Plus C2 E to the minus m times L, okay? And so that term in the square brackets there is just our general solution for theta evaluated at x is equal to L. Okay? And on the right-hand side here, we're going to have, the derivative of that, okay? And so if we take the derivative of this general solution right here, we're going to get an m is going to come out in front. And so we're going to have k times m, okay, times C2 e to the minus m times L minus C1 e to the m times L. Okay. So there's a few negatives that happened right there. So we had this first negative that comes through and cancels, that distributes through there. And we also had another negative that came out by taking the derivative of this negative exponential term, okay? And so the C2 term ends up positive because we have two negative terms that cancel out. And then our C1 term ends up negative because we just have that one negative come from the boundary condition, okay? Okay. And so what we're going to do now is that in this kind of monstrosity of an equation, we're going to plug in for C1. Okay. And so wherever we see a C1, we're going to plug in this expression right here. So we have a C1 right here and a C1 right here. Okay. And so what that will allow us to do is it'll allow us to solve for, C2, because we will have eliminated C1 from the equation. And then once we solve for C2, then we can go back and solve for C1. Right? Okay. Any questions on this before I start writing that out? Okay. All right. And so after we plug in for C1, we end up with this expression. So we have H times theta B minus C2 times e to the ml plus C2 e to the minus ml, okay, is equal to k times m times C2 e to the minus ml minus theta b minus C2 e to the ml. Okay. All right. And so now we've plugged in for C1. And so now, what you'll notice is that the only unknown in this equation is C2. Right? Everything else is either a known quantity or it's our boundary condition. Right? So theta b, we know what that is. M, we know what that is. H, M, K, we know what all of those guys are. Okay. And so now the goal is to manipulate and solve for C2. Okay. Okay. And so first thing I want to do is I'm going to put or what did I do first? Okay, so first thing I'm going to do is I'm going to distribute basically these guys too, okay? Just so that, we have everything like that. And I'm going to move Km over to the other side of the equation. Okay, and so on the left-hand side, we're going to have H over Mk, okay, times the quantity, theta b, times e to the ml, plus C2. And then I'm going to group the two C2 terms together. And so our C2 term is going to be e to the minus ml minus e to the ml. Okay. Right. So that's everything on the left-hand side. And on the right-hand side, I'm once again going to combine the C2 terms. And so we have C2 e to the minus ml plus e to the ml. Okay. And then minus theta b e to the ml. Okay. And so the reason I do this is so that we can put all the C2 terms on one side of the equation, and then we can put all the other terms on the other side. Okay. And so in fact, I'm going to go ahead and move all the C2 terms to the right and then all the non-C2 terms to the left. Okay. And so I'm going to take this guy right here, is C2, e to the minus ml minus e to the ml. I'm going to go ahead and move that to the left, to the right-hand side. And then I'm going to take this theta b, e to the ml, and then move it to the left-hand side. Okay. All right. And then here is the result. And so on the left-hand side, what we have is theta b times e to the ml times h over mk plus 1. Okay. And this is equal to C2 times h over mk. Sorry. Square brackets here. C2 times the quantity of h over mk times e to the ml minus e to the minus ml. Okay. Plus quantity e to the minus ml plus e to the ml. All right. All right. So remember, so for this step, all I did was just move all the C2 terms to one side and all the non-C2 terms together, because now what we can do is we can take this quantity that I'm going to highlight in purple, and then we can divide through on both sides and then solve, and this will allow us to solve for C2. Okay. Okay. And so if we divide through by that, then we have our final expression for C2. And so our C2 here is going to be theta b times e to the ml times h over mk plus 1. Okay. All divided by h over mk times e to the ml minus e to the minus ml plus e to the minus ml plus e to the ml. All right. So it's a little bit intense, I know, and we're not done yet. So we're about halfway done. All right. Any questions on this so far? Probably you guys are still writing stuff down, so I'll give you guys a minute to write this down. Okay. Okay. So now that we've solved for C2, we can go ahead and plug this back in and solve for C1. Okay. Because remember, C1 was nothing more than just C2 or theta b minus C2. Okay. Okay. And so C1 is going to be theta b minus C2. Okay. And then if we plug in C2, we get theta b minus theta b times e to the ml times h over mk plus 1, okay, divided by h over mk e to the ml minus e to the minus ml plus e to the minus ml plus e to the ml. Okay. All right. And so technically this is C1 right here, but we like to usually put it into, under one common denominator. Okay. And so if we do that, then we get the following. Okay. Then we get C1 is equal to, I'm going to factor out theta b because you can see that both of these terms here have theta b, right? And so we go ahead and pull those out of the equation. Right? Right. And so we get theta b is equal to h over mk times minus e to the minus ml plus e to the minus ml, all divided by h over mk e to the ml minus e to the minus ml plus e to the minus ml plus e to the ml. So that's C1, okay? And so now that we have C1 and C2, we can go ahead and plug this back into our expression, okay? Okay. All right. And so after you plug it in, you get kind of this this monstrosity of an equation. Okay. So I'm skipping a couple steps here just because we're almost out of time, and I do want to show you the graph, which is kind of the more important thing. But if you want to see kind of all the details of this derivation, it's in my notes. Okay. Okay. And so our final answer after we plug in for C1 and C2 is we get theta of x is equal to theta b times e to the minus L minus x plus e to the m L minus x, okay, plus h over mk times e to the m L minus x minus e to the minus L minus m L minus x, okay, all divided by h over mk times e to the ml minus e to the minus ml plus e to the minus ml plus e to the ml. Okay. All right. So that's our temperature distribution. Okay. And so what I'm going to do on the next page is I'm going to plot it out. Okay. And so you'll see basically the general trends, which is ultimately what's more important. What I did want to do was I wanted to show you just the math of going through and solving for these constants using these boundary conditions, because once I introduce the other tip boundary conditions to you in the next class, you'll know how to solve for them. Okay. Okay. So before I show the graph, are there any questions on this?
Real quick, just that top right exponential.
That was horrible.
Yeah, yeah.
Was this done by a French guy?
That I don't know.
Because usually the hard stuff is usually associated with some French name.
Yeah, so that last exponential there is e to the minus m times L minus x. So unfortunately, it's really hard for me to get into that corner on the iPad, but yeah, it's basically the same as this term right here. And so this guy is the same as this guy right here. Yeah.
Gotcha.
Yeah. Okay. All right, so let's look at the graph. So this is you know, I whether you remember all these mathematical details is kind of, you know, not as important to me, because what I really want you to get is kind of the intuition for, you know, what this is. Okay. And unfortunately, you know, you can't explain the story of this graph without going through those without going through that derivation. Okay. Actually, it's more kind of like this. Okay, and so if you plot theta as a function of x, it kind of looks like this. So it kind of looks like a decaying exponential, which is kind of what we have in the solution there. Okay. Okay. And so if you remember kind of what our theta represents, and so our theta, remember, represents our excess temperature. And so as you can see, as you go along the fin, as you go from the base of the fin to the tip, theta is decreasing. Okay. And so what that means is that as you go along the fin, you know, the temperature difference between the fin and the fluid is decreasing, right? And this makes sense because, you know, as you go from the left side of this fin right here, you know, over here, you know, we have a big temperature difference between, you know, the fin and the fluid. And so what you're going to have is heat that's going to be lost to the fluid just like that. Okay? And then as the fin loses heat, it's only natural that the temperature actually goes down, right? And so what tends to happen is that at the base of the fin, you have a really high difference between the fin and the fluid. And so you have a lot of heat transfer that goes there. But then as that heat transfer occurs, you know, you have less heat to go around by the tip of the fin. Okay, so the temperature generally goes down. And so the tip of the fin is always going to be cooler than the base of the fin, right? And so, you know, you have kind of those two things. So as the temperature decreases in the fin, as you go from the base to the tip, so does the amount of convection heat transfer, right? And so at the base, remember, so this is kind of the upshot. So at the base of the fin, you have maximum temperature difference and maximum heat transfer. And at the tip of the fin, you have minimum temperature difference and minimum heat transfer. Okay. Okay. Any final questions on this?
Sorry, could you just repeat that maximum, minimum, base?
Yeah, definitely. And so at the base of the fin, so on the left side here, you can see we have maximum temperature difference, right? And so this graph here reaches a maximum, right? And that's because, you know, the base is always going to be where the fin is the hottest, right? And wherever you have maximum temperature difference, you also have maximum heat transfer, right? Because the bigger the temperature difference is from your fin to the fluid, the more heat is going to be lost from the fin going to the fluid, right? Whereas if you compare it to the tip of the fin, at the tip of the fin, we have very little, you know, temperature difference out there, right? And so at the tip of the fin, because the fin has already lost so much heat, we have minimum temperature difference and minimum heat transfer. All right. Okay, so we're a little bit over time, so you know I'm going to call it here today. So so thanks for sticking around for a couple extra minutes, and thanks for going through that lengthy derivation with me. And so remember, Monday is a holiday, so we're not going to have a lecture on Monday, but I will have office hours. So if you want to come by and ask questions of the homework, or if you want to see all the gory details of this derivation, you know, I'm happy to talk about that there as well. Okay, and so have a great long weekend, everyone. You know, rest up. You know, stay safe. Have a great weekend. I'll see you on Wednesday.
All right. Thank you, Professor. Have a good day.
Thanks, you too.
Professor.
Thanks, guys.
And I can email you if I have any questions.
Yes, yeah, you can email me as well.
Professor, I had a quick question.
Sure. What's up?
I can't even find where it was. Oh yeah, okay. So when you said, oh my God. Actually, I don't even know. There was an H theta L. equals negative k and derivative of theta of x. And the next line you wrote, let me see if you have it up right there. I think, yeah, right there.
Okay.
So at the bottom where it says h, and then inside parentheses it's C1 EML plus C2 minus
Yep.
ML
Yep.
equals the KM.
Yep.
Where did that M come from? Where the
Yeah.
K?
Yeah. Good question. So this M right here comes from the fact that we're taking the derivative. And so it was a detail that I kind of glossed over a little bit, right? And so this M comes from the fact that we're taking the derivative of theta, right? Because remember, our theta of x is equal to C1 e to the mx plus C2 e to the minus mx, right? And so when we take the derivative of this, we're taking the derivative of C1 e to the mx. And so when we take the derivative of e to the mx, that m kind of pops out in front, right? When we take the derivative.
Got you. Okay, that makes sense. Okay, thank you very much.
Yep.
Have a good one.
Yeah, you too.